course, since we just talked about exponentials, now we're going to have to talk about logarithms. So every exponential function b to the x is 1 to 1. You can tell just by looking at the graph, right? It looks either like that if it's exponential growth, or like this if it's exponential decay. These functions are 1 to 1 because they pass the horizontal line test, right? Every horizontal line intersects these graphs at most once. So these functions are 1 to 1, and that means that they have inverse functions. And the inverse function is called log base b. So the key thing about logs is that they are inverses to these exponential functions. And remember, that tells you that log base b of b to the x, right? Here we have a composition of inverse functions, right? This is a function composed with its inverse like this. And what an inverse function means is if you compose it this way, you just get back what you started with, right? So that's all this equation really says. And also, if you compose them the other way, you just get x again. So this is saying f inverse composed with f of x is x, right? Okay, so if the bases of your exponential and your log match and you put one inside the other, they just undo each other. Notice that this means that logarithms extract exponents, right? This equation right here, if we had, say, log base 3 of 3 squared, what this is saying, because the base inside and the base of the logarithm outside match, this just extracts that exponent. So this is one good interpretation for what logarithms are doing. They just extract the exponent that would be up here if your base matches the base of the logarithm. So in some examples, you can use this to explicitly evaluate logarithms. So for example here, what is log base 2 of 64? Well, if we can write 64 as a power of 2, then we can just use this property here. So fortunately, 64 is a nice power of 2. So let's see, I'll count the power of 2. So first power of 2 is 2, and then 4, 8, 16, 32, 64. So it's 2 to the 6th. Okay, but then log base 2 just plucks off the exponent. So that gives us 6. All right, what about log base 5 of 1 over 25? Remember, the goal here is to write the stuff inside the parentheses as some power of 5. What power goes here? Well, it's going to have to be a negative power because, right, we have a fraction here. And 25 is 5 squared, so we need a negative 2 here. And then the logarithm base 5 just plucks the exponent off of the exponential with the base of 5. All right, another thing to know about logarithms is what their graphs look like. Well, just like there are 2 flavors of exponential graphs, there are 2 flavors of logarithm graphs. So when b was less than 1, remember b has to be bigger than 0, b to the x looks like this. And something you might remember about inverse functions is the graph of an inverse function looks like the graph of the original function, but reflected over the line y equals x. So this horizontal asymptote x equals 0, that when you flip across this diagonal line, it gets flipped to a vertical asymptote y equals 0. Okay, this intercept right here, it turns out it's 0, 1, that gets flipped to the intercept 1, 0. Okay, so I guess I need to make this go upwards more sharply, like this. And then I got this all backwards. I'm drawing the other flavor of exponential functions. Back up. Okay, so this exponential function, this is exponential decay, like this. Okay. So when we flip this across the line y equals x, this asymptote at x equals 0 gets flipped to the asymptote y equals 0, but since it's a little bit above its asymptote here, it's a little bit to the right of its asymptote way up here. Okay, now this intercept gets flipped to an x-intercept here at 1, 0. So it comes down like this, and then off to the left, it goes up to infinity, and that means off to the right, it sort of swoops downward like this. Now, in the exponential graph, it goes up very quickly, and that means on the logarithm graph, it goes to the right very quickly, which means that decreases only very, very slowly. All right, so this is the flavor of logarithm that corresponds to exponential decay. And for the other flavor, so when b is bigger than 1, our exponential looked like exponential growth. And that's the one that I started drawing before. So same intercept, but its vertical asymptote is down here, and then it goes like this. And off to the right, it increases very, very slowly, right? It's moving to the right so fast that it's increasing vertically only very slowly. All right. Usually when you're using logarithms, it's with a b value that's positive, so this is far and away the more common logarithm graph to use. There are a couple special log functions, just because usually if you're using logarithms, it's one of these two logarithms. The first one is this notation. It's logarithm with no base written down. And this usually, at least in science and engineering, means log base 10. Okay, this is called the common logarithm. And the other specially named log function is ln. Right? So why is this even a log at all? Well, it's shorthand for log base e. Right? Remember, e is this special number 2.7 something. Turns out it's an irrational number. And this is called the natural logarithm. And that's why the abbreviation is ln. It's because of the natural logarithm. Why is it natural? Why is the natural logarithm called natural? Well, it's because it turns out that the best exponential function is e to the x, and so correspondingly the best natural log function, or the best logarithm function, is log base e, which is what natural log is. So when I say the best, the reason that this is the best exponential, it turns out it's related to the fact that the slope of the tangent line at the x-intercept, or at the y-intercept for e to the x, turns out the slope of the tangent line here is exactly 1. For all other bases, the slope of this tangent line at the y-intercept is either bigger than 1 or smaller than 1. But e is the base that makes that slope exactly 1. And it turns out that that's a pretty important property in many applications.